All right. Go. All right. Hello. Good morning, everybody. I hope you are having an excellent week so far. So today we are going to be continuing on with our chapter 4 work. We started that last week with critical points and local maximums and minimums. And today we're going to be talking about something called inflection points, which is an extension of the work that we've been doing, but now thinking about the second derivative and what that might tell us. There's going to be a review session on Thursday. I will send an email out about that to help practice the critical points and inflection point stuff that we've been talking about last week and this week. Okay, so I'm going to go ahead and switch over to the dot cam. There we go. All right. So we've sort of mentioned inflection points casually in chapter 2, but today we're going to learn about them more formally. How do we find them? How do we determine where they are? And how do we work with them? So let's start by talking about what an inflection point is. So an inflection point is a point at which the graph of a function of f of x changes concavity. So it's where we change from concave up to concave down, or concave down to concave up. So how do we look at this picture and determine where the inflection point is? Well, we're looking for where we change concavity. And so we see that this graph starts concave up and finishes concave down. So we want to approximate the point where we change. So it's roughly halfway between the local minimum and local maximum if we're just sort of eyeballing it. And so this right here is going to be approximately where our inflection point is. Okay, and as a reminder from the previous classes, over here we have a local max. Over here we have a local min. And the inflection point is where we change. And like I said, if you're eyeballing it, it's usually about halfway between a local max and a local min, if you have a picture that looks something like this. So how do we know where to find the inflection point mathematically? So I want you to think about what we know about the second derivative and the concavity of the original function. So as a reminder, this is a picture of f of x. And so we know that when the second derivative is positive, our function is concave up. So over here, where we are concave up, our second derivative is positive. And then we also know that the second derivative is going to be negative when we're concave down. So right at the point where we change from concave up to concave down, that point is where the second derivative equals 0, where it changes from positive to negative or negative to positive. So if the second derivative changes signs around a point, then that point is an inflection point. Okay, we have to be careful. So if you find algebraically that the second derivative equals 0, that is not enough to say it's an inflection point. We need to make sure that the second derivative changes signs. So if you think back to what we were talking about last week with local maxes and local mins, sometimes we had neither, right? So like when we were looking at the first derivative test, sometimes it went negative, negative, or positive, positive, and it was neither, sort of like a weird flat spot. So sometimes the second derivative equaling 0 is also a weird flat spot. So in order to make sure it's actually an inflection point, that's why we're going to make sure that we change signs at the point that we're considering. So what does this process look like? So the majority of the time we will be doing this algebraically. So we will look at a bunch in the beginning that's all algebraically, and then we'll look at what that might look like if it's not algebraically. But our steps are going to be to determine where the second derivative equals 0. So if we have an inflection point, then the second derivative will be 0 there. But then we have to check, right? And then we're going to make sure the second derivative changes signs around possible inflection point. Okay, so how do we do that? How do we check it? Well, we set up a number line and we pick a point to the left and to the right, and we plug it into the second derivative and we check the signs. Okay, so we're going to try one, see how this all works. Okay, so we have this function here. We have 2x cubed minus 3x squared minus 36x plus 14. Find all the inflection points of this function. Okay, so what I would like you to do here is I would like you to find the first derivative and then the second derivative, set the second derivative equal to 0, solve for x, that will give you a possible inflection point, and then test something to the left and to the right in the second derivative to see what the sign of the second derivative is. That's how we're going to check. Okay, so we're going to try this out. It's the first time. I want you to give it a go. It'll be good practice on taking derivatives. I'm going to give you 2 minutes to see if you can find the first and second derivative. Again, second derivative equals 0 and solve. Even if that's the only part you get, if you're not sure how to check, that's okay. We want to get really comfortable solving within the second derivative. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 more seconds. Okay, so as a reminder, if we're looking for critical points, we're using the first derivative. So if we were looking for local maxes and mins, we would look for critical points by setting this equal to 0. However, when we look for inflection points, we are looking at the second derivative and determining where that equals 0 as our first step. So here, the first derivative, we would just use our power rule. We get 6x squared minus 6x minus 36. And again, the 14 will have a derivative of 0 because it's a constant. And so the second derivative, we're going to take the derivative of the first derivative. So here, that'll be 12x minus 6. And so if this function has any inflection points, it'll happen when the second derivative equals 0. So we want to set that equal to solve. So we're going to bring the 6 over, and we get 12x equals 6. We're going to divide both sides by 12. And we get x equals 6 over 12, which equals 1/2. So if we have an inflection point, which we still have to check, it's going to be at 1/2. So let's check if 1/2 is actually an inflection point. So I'm going to draw a number line. And we're talking about the second derivative here. And we know our possible inflection point is that x equals 1/2. Okay. So we know at 1/2, the second derivative equals 0. So we want to test something a little to the left and a little to the right to see what the sign of the second derivative is. So again, you want to pick these points to be convenient and easy to work with. You can pick any point to the left and right of half. So over here, I'm going to pick 0, 0 to the left of half. If I plug 0 into my second derivative, I'm going to get 12 times 0 minus 6. So that gives me -6. Okay. I'm not really as interested in the actual value. I'm interested in whether it's positive or negative. So sometimes you can eyeball it and figure out if it's going to be positive or negative without doing the full calculation. So here I see that this is going to be negative. So in the original function, everything to the left of -1/2 is going to have a negative second derivative. If you have a negative second derivative, this means the original function was concave down. Okay. I also want to test something to the right of half. So I'm going to pick 1. So again, I'm going to go ahead and I'm going to plug in 1, and I'm plugging into my second derivative because I'm interested in the sign of the second derivative. So I have 12 times 1 minus 6, which is positive 6. Okay. If my second derivative is positive to the right of half, that means I'm concave up to the right of half. So that means I'm changing from concave down to concave up. So that means that this is in fact an inflection point because I changed signs. And because I changed signs, that means I changed concavity. So this is in fact an inflection point. We do have to check every single time. There are sneaky ones that are not inflection points. And again, what will happen is you'll have something like plus plus or minus minus, and then you know it's not actually an inflection point. Okay, so we're going to be practicing these types of problems. Now that we've done one through, hopefully this process makes sense. So let's look at another one that's just algebraic in nature. Okay. So here we have the function 3x to the 4th minus 4x cubed plus 6. And we are interested in finding all the inflection points of this function. Okay. So again, you're going to find the first derivative and then use that to find the second derivative. Once you have your second derivative, we want to know when does that equal 0. You will have to do a little factoring on the second derivative. And then once you have that, we want to test to make sure that we are actually changing signs around our inflection point or our possible inflection point. So I'm going to give you about 3 minutes. I want you to try this out. Again, just be a little careful on the second derivative when you're factoring. Try your best. You will find 2 possible inflection points, and then you have to test them just like we did in the last problem. Okay, so try it out, and then we will go through it together in approximately 3 minutes. Okay, take about 30 more seconds. All right. So again, we need to go through the first derivative to find the second derivative. We're using our power rule with polynomials. And so our first derivative, we have 12x cubed minus 12x squared. And then the 6 goes away because that is a constant that's by itself. When we find the second derivative, we're going to get 36x squared. So the 3 comes down to multiply the 12. Minus, now 2 times 12, we have 24x. And we want to know, when does that equal 0? Because those are the possible places we could have inflection points. So there's a couple different ways to solve this. You can use the quadratic equation, you can factor. There's even a couple different ways to factor it. So if you didn't do it exactly how I did it, but you came to the same conclusion, then that's totally fine. So when I factor this function, I'm going to pull out a 12x. Okay. And so for my first term, if I take 12 and there was 36, that leaves me with a 3. And I took 1x, but this was an x squared. So I'm left with a 3x minus. Now, if I pull a 12x out from 24x, that leaves me with a 2. Okay, so that's one way you can factor it. You could also just factor out an x and you will eventually come to the same critical or inflection points that I get. It's really a matter of preference. So I now have 2 factors. And I want to know, when does this equal 0? So I set each factor equal to 0. So for the first factor, I would have 12x equals 0. If I have 12x equals 0, that gives me x equals 0 as the only possible solution. For my second factor, I have 3x minus 2 equals 0. So I can bring the 2 over and divide by 3, and I get x equals 2/3 will make this second factor equal to 0. So those are the only 2 factors. So these are the only 2 possible solutions. Okay. So the question is still, are they actually inflection points or are they weird flat spots? So now part 2, I have to actually check. So the second derivative, I'm going to put on a number line. I want to put these in order. So 2/3 is bigger than 0. Okay, so these are x values. I know that at these particular values, the second derivative is 0. And so now I want to test some points to see if each of these intervals is positive or negative. So again, I'm going to pick points that I think are convenient. So I'm going to start over here to the left of 0. I'm going to pick -1. So just like I did when we were talking about critical points and using the first derivative test, I'm just going to look at whether each factor is negative or positive to figure this out. You can certainly just plug this right into the second derivative in your calculator to figure it out. But the goal is to plug a -1 into some version of the second derivative and determine if that is then going to be positive or negative. So if I plug in a -1 into 12x, that's going to give me something negative. And then if I plug in a -1 here, I get -3 minus 2, which is -5. So that's also negative. And for me, negative times negative is going to be positive. Okay. Like I said, you could just plug it directly into the second derivative. You would end up with 36 plus 24. You would also get something positive. Either method is fine, but we really need to figure out the sign at -1. So now I'm going to pick something between 0 and 2/3 for this second interval. So I'm going to pick 1/3. To me, that's what makes most sense, but you, again, can pick any number between 0 and 2/3. So if I plug a 1/3 into 12x, I'm going to get something that's positive. 1/3 times 3 is just 1. 1 minus 2 is -1. So that stays negative. So positive times negative is negative. And then again, I'm going to pick something to the right of 2/3. So I'm going to pick 1. So if I plug in a 1 into 12x, that's positive. If I plug in a 1 here, 3 times 1 minus 2, also positive. Positive times positive is positive. So now I look at each of my possible inflection points to see if the sign changes around them. So here at 0, I went from positive to negative. So the sign did change, which means the concavity changed. So that is an inflection point. And then here at 2/3, I go from negative to positive. So that also changes, which means the concavity changed, which means 2/3 is also an inflection point. Okay. Now, just like we talked about back when we talked about critical points, you can graph the original function on your graphing calculator and look at what's happening at 0 and 2/3. And you should see that it looks like an inflection point, like the picture we saw at the very beginning. You should be changing concavity at these points. That graph should agree with the work that we're doing here. Okay. Okay. So now that we've practiced classifying inflection points in sort of the standard way, I want to present to you the way that this is commonly put together. So in a lot of instances, the idea of local maximums, local minimums, and inflection points are all packaged together to talk about what the function is doing. So I'm going to give you an example of sort of a typical problem, how that looks with all of this put together, so we can see and practice that. Okay. So find all local maximums, minimums, and inflection points for the function 2x cubed plus 3x squared minus 180x plus 5. So there's a lot of things that are going to happen here, right? We're going to need the first derivative to help us find critical points. We're going to use the second derivative to help us find inflection points. Then we have to classify our critical points. So we could use the second derivative test, since we'll have that. We could use the original function or any of the tests really to classify those critical points. And then on the second derivative side, we will have to check to make sure anything we think could be an inflection point is actually an inflection point. So this is tying in what we were doing last time with the stuff that we're doing this time. And this, like I said, is a very common way for these things to be packaged together. So this is something that you will see both on homework, as well as a quiz, as well as if this comes up in your particular major, these things, local maxes, mins, and inflection points are usually done all together. Okay, so there's a lot of steps in this one since we're asking for a lot of information. So I'm going to give you, let's see, we'll do 4 minutes to try to work it all out. Try to be careful with the algebra. And if you have time after you've solved for these things, I strongly encourage you to graph this function and make sure that what you're saying mathematically agrees with the picture of this function. Okay, so try it out and then we will go through it together. Okay, take about 30 more seconds. Okay. So one of the things that really is going to help us here is to try to stay organized with all of our work. So I'm going to do my best to try to stay organized, but I encourage you to think about how you can write up your work in a way that you can easily go back and check things if you need to. So I'm going to start with the first derivative. So the first derivative here is going to be 6x squared plus 6x minus 180. Okay, hopefully by this point, you're feeling very comfortable with these types of derivatives. Obviously, they come up a lot in the work that we do. So again, if you're still not super comfortable with those, you may want to practice those a bit more. So once I have the first derivative, I want to use that to find my critical points. So I'm going to ask the question, when does this equal 0? So first derivative, again, gives us critical points. So in order to figure this out, I'm going to factor this. And again, there's a couple different ways you can deal with this. So if you decide to use the quadratic equation or something else, that's totally fine. But as you probably have noticed, I prefer to factor. So I'm going to get 6 times x plus 6 times x minus 5 equals 0. Which means that my possible critical points here, my local maxes and mins, are going to be at x equals -6, which will make this first parenthesis 0, and x equals 5. So these are my critical points. Okay. And I don't know yet if they're local maxes and mins, but I do know that they are critical points because that's where the first derivative equals 0. Okay. Now, I also am going to need the second derivative to talk about inflection points. And so I'm going to do that over here. So my second derivative, I'm going to go to my unfactored first derivative and take the derivative of that. So the derivative of 6x squared is 12x. The derivative of 6x is 6. And the derivative of 180 is going to be 0 because that's a constant. Okay, so in order to talk about inflection points, I want to know when does that equal 0. So if I solve this, I can subtract the 6 over and divide by 12. And I get x equals -1/2 as a possible inflection point. So I'm going to put inflection point, question mark, right? Because I haven't tested it yet. So I have a choice now. Right? So there's a lot of different ways that we can classify critical points, right? We have the original function, the first derivative test, and the second derivative test. All of them will give us the same result. It does not matter which test you use here. All of them can be used in this situation. Because I already found the second derivative to talk about inflection points, I'm going to use the second derivative test to classify my critical points. And again, you don't have to do that. You don't have to pick that test. But for me, it makes sense. And I particularly think that this won't be too terrible to plug things into. So I'm going to plug in -6, which is my first critical point here, into the second derivative. So I have 12 times -6 plus 6. And that's going to give me -66. Okay. And what the second derivative test says is if the second derivative is negative at a point, which is what we have here, that means the original function is concave down, which makes that critical point a local maximum. So here, this is a local max. And then I'm also going to test my other critical point of 5. So I have 12 times 5 plus 6, which gives me positive 66. The second derivative test says that if your second derivative is positive at your critical point, the original function is concave up, which makes that critical point a local minimum. So now I know that -6 is a local max and positive 5 is a local min. One of the other reasons why I like to use the second derivative test here is because it's also going to help me with my inflection point analysis. Okay, so I know that I have to test points on either side of -1/2, but I already did that with these critical points, right? So -6 is to the left, and at -6 I was negative. Positive 5 is to the right of -1/2, and that gave me something positive. So I can see I can use the signs from this test to also determine that this is indeed an inflection point because it changes signs. Okay, if you didn't notice that, you could certainly pick 2 points to test. You could do like -1 and 0, and you will get the same result. Okay, but if you use the second derivative test to classify your critical points, that also will give you information you can use to check if your possible inflection point is an inflection point. So here, the final result is that we have a local maximum at x equals -6. We have a local minimum at x equals 5, and we have an inflection point at x equals -1/2. Okay, and so again, it's very common that these things are done together. Okay, so those are sort of the common computational ways that we think about inflection points. The next problem that we're going to look at is going to bring in some conceptual thinking about what we know about critical points and inflection points, as well as some computational aspects of taking derivatives. This one's a little bit tricky to think about the first time through, but we do have everything we need to solve it. So here it says to find a formula for a cubic polynomial, ax cubed plus bx squared plus cx plus d, that has a critical point at x equals 4, an inflection point at 2, 5, and a leading coefficient of 1. So there's a couple things I want to say about this before I send you off to try it. A leading coefficient means the number in front of the term with the highest power. So the leading coefficient here is a, which just means that a equals 1. What we are trying to solve for in this problem is the values of a, b, c, and d. Okay. We are told that we have a critical point at x equals 4. Typically, we are solving for the critical point. We are trying to determine what x value is the critical point, but here we are told what the x value is. So we're using it in a slightly different way. So think really carefully about what that means in terms of critical points. And then inflection points, I want to point out that when we talk about the inflection point in terms of the second derivative, we are only ever looking at the x value, and that this point, 2, 5, is the point on the original function where that inflection point is. So we will only be using the x value when thinking about the second derivative. So when you do this, my recommendation is that you start by finding the first and second derivative before you apply what you know from this problem. Okay, you can sub in a equals 1 to start, but then find the first and second derivative generically, and then see how you can use this information to try to solve for the other constants. Okay, so we know that a equals 1, but we still need to find b, c, and d. So I'm going to give you about 3 minutes to try this out, see what you can figure out. Even if you get it wildly wrong, that's still really good because we learn and practice derivatives. We learn what doesn't work. And if you get it right, great. Okay, try it out. I'll give you about 3 minutes and then we'll go through it together. Okay, take about 30 more seconds. Okay, so again, if we have a leading coefficient of 1, that means that A equals 1 because A is the coefficient in front of the term with the highest power. So we're trying to find B, C, and D. So if we take the first derivative of this function and we know that A is 1, then we get 3x squared as the derivative of the first term plus 2bx here, because we don't know the value of b, so that's got to be part of our constant, plus c, right? The derivative of d is 0 because d is a constant that's by itself. We also want to find the second derivative, and hopefully you'll be able to tell why I recommended that in a few minutes. But here, when we take the derivative, we get 6x plus 2b. The derivative of c goes away because, again, now c is a constant that's by itself. So we have information about the critical point at x equals 4 and the inflection point. So what I want to notice here is that in the first derivative, there are two unknowns, b and c, which means knowing something about the critical point is not quite enough. Whereas the second derivative has only one unknown here, which is the b. And I know you may be thinking, well, x is unknown, but we actually do know something about the x value from this statement here. If we have an inflection point at the point 2, 5, then that means that when x equals 2 from this point here, that the second derivative should equal 0. So when x equals 2, again, from this point here, we get 6 times 2 plus 2b equals 0. So we have 12 plus 2b equals 0. And if we solve that, we get b equals -6, right? So we subtract the 12 over and divide by 2. So now we know b equals -6. So now if we go back to the first derivative, we can plug in that value for b, okay? So now my first derivative will be 3x squared. Now remember, b is -6, so -6 times 2 will give me -12x plus c. So I've plugged in this b value into my first derivative. And so now I want to use that to solve for c. Okay, how do I use this? Well, now I'm going to use the fact that we have a critical point at x equals 4. So how does that work? This is slightly different than the way we usually use critical points, right? And so what this means is that if I were to plug a 4 into the first derivative, it should equal 0. Because remember, critical points are where the first derivative equals 0. So if we have a critical point at x equals 4, that means if we plug in a 4, the first derivative should equal 0. Okay, and again, this is slightly different than the way we normally use critical points. So it takes a little bit extra sort of thinking and analysis to figure that out. Okay, so if we crunch these numbers, 4 squared is 16, 16 times 3 is 48. 12 times 4, also 48, plus c, and because we plugged in a critical point, that would have to equal 0. Well, 48 minus 48 is 0, so we get c equals 0. Okay, so if this was a different number, we would just bring it over to the other side. But in this case, we find that C equals 0. So now we have a value for A, we have a value for B, and we have a value for C. What's left is we need to figure out what is the value for D. Okay, and this one is a little bit tricky. Let's see. We can do it on our, we'll do it on this side of the note card here. So let's put together what we know so far, right? So we know f of x equals x cubed, because A is 1, minus 6x squared plus 0x, so that zeroes out, plus D, right? So if we plug in the values we know, we get a function that looks like this. And so now this is where we go back to this inflection point. Okay, I mentioned in the setup that the inflection point is the location on the original function, which means that this point 2, 5 is a point on the original function. That means we can use it to solve for D. So this says when x is 2, y is 5. So we have 5 equals 2 cubed minus 6 times 2 squared plus D. Right? So we have 5 equals, this is going to be 8 minus 24 plus D. 8 minus 24 is negative 16. So we're going to add 16 over to the other side, right? 16 plus 5 gives me a D value of 21. So now we have the value of A, B, C, and D. And so my final equation, when I put that all together, is f of x equals x cubed minus 6x squared plus 21. Okay, so again, this is sort of the intersection of calculations plus definitions and operationalizing the definitions to be able to use this type of information to solve something a little bit different. So again, it's important that we understand the definition of critical point and inflection point to be used in a variety of ways. Okay, so that is that one. The next problem that we're going to look at sort of bends towards more analytical. So we're not going to be computing things. We're going to be analyzing some information. It sort of spans over 2 pages. So let me, I don't know why I printed it like that. That was goofy of me. So here's what we're working with here. Okay, so we have this chart that is going to give us information about the first derivative and the second derivative. And so this is what's happening at different values. So 0, 1, and 2. So what we're told is that the first derivative is 0 at 0. The first derivative is 0 at 2. And then we have the signs of the first derivative in between. And then for the second line chart, we have information about the second derivative. And so we want to use this information to try to talk about where this function has critical points and where it has inflection points. Okay, so I want you to take a look at this and the information we have about the first and second derivative and see what you can say about the critical points and inflection points. Okay, it says justify your answer. So you really just want to talk about how you know it's a critical point or an inflection point based on some of the stuff that we have been doing, you know, in the critical point section and in the beginning of class today, dealing with the signs of these things and what they tell us. Okay, so I'm going to give you 2 minutes. Try to look at it, think about what it tells us, and then we will go through it together. This may or may not stay here. Let's see. Stay here, maybe. Okay, there we go. Okay, take about 30 more seconds. Okay, just gonna move this down here so we can write on it easily. So as a reminder about notation, when we talk about y prime, that's the same thing as f prime of x. And then when we talk about y double prime, that's the same thing as f double prime of x, right? Those mean the same thing. So what we see here is where the first derivative equals 0, so at 0 and 2. So that means that at 0 and 2, those are critical points, right? So that's the first piece of information we have. We have critical points at x equals 0 and x equals 2. That's where the first derivative equals 0. Now, we can try to see if we can figure out what types of critical points these are by looking at how this changes. So here, the first derivative is greater than 0, so it's positive. Here, the first derivative is greater than 0, so that's positive. And then here, the first derivative is less than 0. So what we see is that the derivative sign doesn't change at 0. Right? So x equals 0 is not a local max or a local min because it didn't change signs. However, at x equals 2, we see that the first derivative changes from positive to negative, which means the original function was increasing and then decreasing, which makes 2 a local max. Okay, so again, x equals 0 was not a local max or a local min, but x equals 2 is a local max because the sign of the first derivative changes from positive to negative. Okay, so now on the second derivative, we see that the second derivative equals 0 at 0 and 1, which means at 0 or 1, we could have an inflection point, right? If the second derivative equals 0, we could possibly have an inflection point, but we need the sign to change. So what we notice here is that the second derivative is negative to the left of 0, that it's positive to the right of 0, and then it's negative again when we go to the other side of 1. So that means in both of these instances, at 0 and at 1, the sign of the second derivative changes, which means that we're going to have inflection points at both 0, so this is the x equals 0 line, and 1. So we have inflection points at 0 and 1, and we have a local maximum at x equals 2. So that's how we read these sorts of charts. We've constructed these sorts of charts for both critical points and inflection points, but now we have a double chart where we talk about both. So that's how we analyze that type of information. So as we sort of continue thinking about how we analytically apply these rules, the next example that we're going to look at is going to be this graph. And it may look familiar because we've looked at this graph before in the last class to talk about things like critical points. So what are we trying to do here? We have a graph of the first derivative of a function, okay? And it spans the interval -2 to 8. So if we have the graph of the first derivative given below, we want to use this graph to find the inflection points of the original function. So the question is, how do we use information about the first derivative to tell us something about the second derivative? And what do we need to know about the second derivative to find inflection points of the original function? So there's a lot of things happening here that we have to think through about how we might be able to use this first derivative to then give us, again, information about the second derivative to then link back to the original in terms of inflection points. So again, this is just really thinking about the analysis of it all. So I'm going to give you about 3 minutes to try to think it through, 2-3 minutes, see what you can figure out on how these might relate, and then we will go through it together. Okay, take about 30 more seconds. All right. So if we're looking for inflection points of f of x, we know that one of the ways we start to think about this is trying to figure out where does the second derivative equal 0. Okay, so that's sort of the key connection here. So what we have is a graph of the first derivative. So the question then becomes, how do we figure out where the second derivative equals 0 based on the first derivative graph? So in order for the second derivative to be 0 based on the first derivative, we would need to find where the tangent lines are 0 on the first derivative graph, because that'll tell us where the second derivative is 0. Remember that when we have a slope of 0, that's when we have horizontal tangent lines. So we are looking for the places where this function has horizontal tangent lines. Okay, so when we have horizontal tangent lines, that's when the second derivative equals 0. But again, it's not enough for the second derivative to equal 0. We need the second derivative to change signs around our point. So how do we check that? So this is where we then use the relationship about the sign of the second derivative and whether the first derivative is increasing or decreasing. So if your first derivative is decreasing, then your second derivative is negative. So that happens here and here. Okay. If your first derivative is increasing, which happens here and here, that tells us that the second derivative is positive. So what we see here is that our second derivative changes signs at each of these 3 points. right? It changes from positive to negative, negative to positive, positive to negative, which means each of these is in fact an inflection point. So then we would just approximate where they are. So we'd say x equals negative 1.5 is an inflection point, right? This is like x equals 1.5, maybe 1.6. We're just approximating here, right? This looks like maybe x equals 4.75, right? But we checked that things change, and we are using a lot of analysis on all the different rules of how all of these three functions interact. So that's how we would go about locating inflection points of an original function based on the graph of the first derivative. Okay, as you can probably guess, the next problem will be to look at a table and to do something similar. So suppose that f of x is a continuous function that's differentiable. Given the table of values of the derivative, determine the most likely places that f of x would have an inflection point. Okay, so again, we're looking for inflection points of f of x based on a table of f prime of x. Let's see, f of x has inflection points or an inflection point at, okay, so how do we look at a table and then do the same type of work to really think about where the inflection points might be? Okay, so I'm going to give you 2 minutes. Think about this. Think about where we think this may happen. Okay, again, we want to use the first derivative to really think about the second derivative and think about how we may do that to try to figure this out. Okay, so try it out, see if you can make those connections, take about 2 minutes, and then we'll go through it together. It may be helpful to look back at what we did with the graph when you're trying it out. Okay, take about 30 more seconds. Okay, so I'm going to refer back to the graph for a moment to point something out to you. So notice that we had inflection points when our function changes, when our first derivative changes from increasing to decreasing or decreasing to increasing. okay? Because that impacts the sign of the second derivative. So that's what we're going to look at here. So I want you to notice that as we start checking out these values, we have -14, -8, -4, 0, 5. Those values are all increasing, okay? If they are increasing, that tells me that my second derivative is positive. And then what happens is those values go from 5 to 2 to -1, which means that they are decreasing. If your first derivative is decreasing, that tells us that the second derivative is negative. So at the point where we change from positive to negative, we have to turn around, right? Or we have to go through the axis. So that means that x equals 8 is the most likely place we have, given the current information, that the second derivative would be 0, because this is where we change signs from positive to negative. You may have been tripped up by this 0 here, but that's a 0 on the first derivative, and inflection points have to do with the second derivative is 0. So what we're looking for again is where the first derivative is increasing and decreasing, because that links to the sign of the second derivative, which helps us figure out where we change signs, which is where the most likely place we would be 0 will fall. So here, x equals 8 is our most likely place for our contender for an inflection point based on the information that we have. Okay, so that's the end of the examples for today. So go ahead and try out some of the homework before you do the mini quiz due on Wednesday. And hopefully this sort of overview of all the different types of inflection points will help you be very prepared for these types of questions. But again, driving home the fact that we need to really understand all the relationships between f of x, f prime of x, and f double prime of x, as well as definitions to be able to complete our work. Okay, have a great rest of your day, and I will see you all on Thursday.